Now I will discuss question number 11. I will draw the diagram. It's like this. A non-viscous fluid of density D has streamlined flow through horizontal pipe of variable cross-sectional area as shown in the figure. If the pressure of fluid is P at the point where the velocity of flow is V. They have given that pressure at this point is P. What is the pressure at another point? Velocity 3V. We have to find the pressure at a point, velocity 3V. It should be a point like this. Because of, we know that when cross-sectional area decreases, velocity increases. We have to find pressure at this place. I will consider it as P dash. Now we can use Bernoulli's principle between x and y points. Pressure plus half rho v squared plus x rho g equals to, for point x, should be equals to pressure plus half rho v squared plus x rho g for point y. Now we know that these 2 points are in the same horizontal level, then x rho g constant. Pressure at x, P dash, we have to find it. Half rho 3v squared means 9v squared. Should be equals to P plus half rho v squared. Density is given as D, therefore we can substitute D for the density value. Now we have to subject P dash. P dash equals to P plus half dv squared minus half d9v squared. Then we can simplify it. P, there are opposite marks for this term, mark of the large term minus, we have to subtract half into d into 8v squared. Divide by 2, 1, 4. Then P minus 4 dv squared. Second answer is correct for the question number 11. Question number 12. Non-viscous incompressible fluid steadily through the pipe shown in the figure. The variation of the flow speed of the fluid along the tube from A to F is best represented by. Tube A has the smallest cross-sectional area, part A to B. Therefore, we can observe maximum velocity from A to B. And area from B to C is greater than the area from A to B. There is a same cross-sectional area from D to E. It means B to E, there is the same cross-sectional area. Therefore, velocity from B to E should be a constant value and it should be less than this velocity from AB part. And the largest area is for the tube EF. Therefore, area of EF should be less than velocity of EF part should be less than these two parts. Then we can get fourth answer is correct answer for the question number 12. Then 13. A major artery with 1 square centimeter cross-sectional area and blood branches into 18 small arteries, each having a cross-sectional area of 0.4 and carrying equal volume of blood per unit time. The ratio speed of blood in the major artery divided by speed of blood in small artery. You can consider if the large artery is this one, and if it is divided into 18 small arteries, AV should be constant. Then cross-sectional area for large artery 1 square centimeter multiplied by velocity at major artery V1 should be equals to AV for small arteries. Cross-sectional area for one small artery 0.4. There are 18 arteries. Therefore, we have to multiply by 18 to get the total cross-sectional area. And velocity for this small artery V2, AV should be constant. Now we have to find the ratio between V1 and V2. V1 divided by V2. 4 into 18, 4 into 8, 32, 3 remaining, 4 into 1, 4 plus 3, 7. 7.2. Then answer is C for the question number 13. Then question number 14. A large metal sheet bent into the shape shown in the figure is kept upright on the ground by means of 4 stretched ropes into the ground. Magnitude of the tension in all ropes TA, TB, TC, DD in steel air are equal when wind blows through the sheet in the direction XY. Now we can consider, according to the shape of given metal sheet, it is like this. There is a high velocity in this direction. It is the reason for bending. Therefore, for this side, velocity is a higher value, pressure is a small value relative to opposite direction, opposite side. Then we can get tension at A should be greater than tension at B, because of there is a high pressure in this side. The sheet will try to move in this direction. Then we can get tension at this arrow TA is greater than TB. Same method, we can get tension at D. Tension at D should be greater than tension at C. Then answer is 2 for the question number 14. Then 15. A cylindrical tank having a very large diameter contains two immiscible liquids of density D1 and D2. They have given that D1 greater than D2. The tank has a small hole closer to the bottom. If the height of the liquids at a certain instant are H1 and H2, what will be the speed V of the liquid ejected out of the tank at instant? Neglect the surface tension effect and assume that liquids are non-viscous. Now there are two liquids. And there is a hole. You have to find V velocity. They have given that there is a very large diagram, very large diameter for the container It means velocity at this point is 0. Then we can get pressure at this point. H1 D1 G plus H2 D2 G. This is the pressure for this point. Plus atmospheric pressure. I will consider atmospheric pressure as P0. Then we can use Bernoulli's principle from between this point and this point, X and Y. When considering X and Y points, we know that there is the same vertical height. It means X and Y points are in the same horizontal level. Therefore, we can use Bernoulli's principle without using H rho G term because of it is cancelling. Then I will use Bernoulli's principle for point X and Y. Pressure at point X, H1 D1 G plus H2 D2 G plus atmospheric pressure plus half rho V squared. We know that velocity for this point is 0 because of we can get there is a large cross-sectional area. Therefore, velocity through this container should be 0. Then half rho V squared term is 0. Then we can use for point Y. Pressure is atmospheric pressure plus half D2 V square. So D1 V square. D1 liquid is flowing out first. Then we can cancel out P0 terms. We have to subject V. Then 2 times G is the common factor, H1 D1 plus H2 D2 divided by D1. Root. It is the velocity. We can simplify it to get the answer. V equals 2G root 2G H1 D1 divided by D1 cancelling, therefore H1 plus H2 D2 divided by D1. We can write it separately. Then answer is 5 for the question number 15. Question number 16. Consider the following physical phenomena. Water flowing through the tube having 2 different areas of cross-section. Speed of water at y, V2 greater than V1. Gradual narrowing of the cross-section of water column falling down freely from the tap. Deflection of a cricket ball which is moving while spinning. Existence of height difference of in the liquid column in vertical tube. Which of the above phenomena can be explained by using Bernoulli's theorem? First one and second one, A and B, we can't use Bernoulli's principle to explain A and B because of it is due to continuity equation. A1 V1 should be equals to A2 E2. It is not the not a result of Bernoulli's principle. But C and D are due to the Bernoulli's principle. Then we can get C and D only. Answer is 3 for the question number 16. Question number 17. Two objects A, B of the shape of the following figure and spherical object C, all having identical masses, are mounted rigidly on a horizontal surface along y-axis by a thin rod as shown in the figure. Both xy axes are located on the horizontal surface. A stream of airflow through the object parallel to the surface and along x direction. Assume that airflow causes no turbulence around the object. The magnitude of forces FA and FB and FC exerted by the object and the sphere on the mounted rods when written in ascending order will be. They have given that the answer, there is no an answer. They have given all for question number 17, but I will explain how to get the answer. A, B, C. There is a special shape for A and B. We know that it is the aerodynamic shape of wings of an aeroplane. Then velocity at this side should be a greater value. Then pressure is smaller than this side for point A. Therefore, weight plus pressure, force due to pressure difference. I will consider it as F. mg plus F is the force exerted due to the airflow for object A. When considering object B, velocity is a greater value for this side, therefore pressure is a smaller value. Then F force is acting in upward direction and mg is downward direction. Then mg minus F. For the spherical surface, we can get that there is no force due to flow. It means there is only one force, it is weight on the rod. Now we can compare force on A is the greatest value. Then C is next one and B is next one. We have to write ascending order. FB, FC, FA. Then second one is the correct answer. But I think that there is a problem with given figures. Therefore, they have given that all for question number 70. Then 18. A pipeline laid horizontally carries a liquid of density D at a constant speed V from pressurized large overhead tank. Pipelines passes through a shallow region of the muddy water as shown in the figure. Pressure above the liquid surface in the overhead tank is P and the atmospheric pressure P0. Suppose a small crack has been developed on the pipe at X the condition for muddy water to seep into the pipe. Assume that liquid level in the tank is maintained at constant height h from the ground, and that the seeping of muddy water does not change speed v. There is a crack. Then we can use Bernoulli's principle to get the pressure inside the tube at x. We can use Bernoulli's principle between x and y points. Pressure at x, P. There is no velocity given in this point, therefore we can get half rho v square term is 0. We can consider that there is a large cross-sectional area. Plus h rho g. H rho density is given as d. G should be equals to pressure at y plus velocity v, then half rho v squared. H rho g is 0. Now we can get pressure at y, P plus HdG minus density is d, half dv squared. Now they have given atmospheric pressure is P naught. Therefore, pressure for this point is P naught. If there is a flow into the pipe, P naught should be greater than pressure at y. P naught should be greater than P plus HdG minus half dv squared. Then answer is 3 for the question number 18. Then question number 19. Consider a non-viscous and incompressible fluid moving with steady streamline flow through the tube of non-viscous, non-uniform cross-sectional area. In a vertical plane, figure shows the vertical cross-section of the tube XYZ. Represent 3 points of streamline. Area of cross-section of tube X is same as Z. Consider the following inequalities for the relative magnitudes of kinetic energy per unit volume, potential energy per unit volume, and fluid pressure at the Px, Py, Pz positions. We know that velocity at y should be greater than x and z because of there is a small cross-sectional area. Therefore, kinetic energy at point y is greater than x and z. But we can't compare kinetic energies for point x and z. Should be same. We can get statement A is incorrect because of kinetic energy at x should be equals to kinetic energy at point y. When considering potential energy, we know that x is the lowest level. Therefore, potential energy at x is the smallest value, then z, y is the highest point, then y. B is correct. Statement C. Pressure at y less than pressure at z. Yes, we know that velocity is a higher value. Therefore, pressure at y is smaller than z. But when considering point x and z, for the point z, potential energy is a greater value. if the potential energy H rho g term is a greater value, pressure we can get P plus half rho v squared plus H rho g constant. When considering x and z points, there is the same velocity, therefore kinetic energy is constant. When h is a greater value, p should be a small value. Then pressure at z should be less than pressure at x. Then C also correct, B and C correct. Fourth one is the answer for question number 19. Then 20. The human blood circulatory system consists of about 1 million capillary vessels, each with an average diameter 8 micrometers. If the blood is pumped from the heart at rate 5 liters per minute, what is the average speed of blood flow through the capillary vessels in centimeters per minute? We can get AV into N, number of capillaries, 10 to the power 9. AV into number of capillaries should be equals to 5 liters per minute. It means 5 divided by 1000 cubic meters per minute. Then we can convert cubic meters to cubic centimeters. We have to multiply by 10 to the power 6. Now we can cancel out 10 to the power 6. Cross-sectional area is pi r squared. Phi radius is given as, diameter is given as 8 micrometers. Then radius 4 micrometers. But they have asked in centimeters, therefore we can convert this meters value to centimeters. When converting meters to centimeters, we have to multiply by 100 into this 10 to the power 3 value. 5 divided by 1000. We have to substitute square of radius. Therefore, we have to put square. This is the area. We have to multiply by b. Then we have to simplify it. b equals 10 to the power. We can simplify 10 to the power value. 5 divided by 1000 divided by 5. 4 squared 16. 10 to the power minus 4 squared 10 to the power minus 8 into 10 to the power 3. 3, 6, then 10 to the power minus 2. We can get it 500 divided by 16, 5. Divide by 4, 4, divide by 4, 125. Then 125 divided by 4, 5 is the answer. This one is correct for the question number 20.